In this video, we're going to talk about equations of lines. So I've drawn a line here, and it passes through 2 points, A and R. If you were given the coordinates of those points, you could express the equation of that line in Cartesian form. Whether you use slope-intercept form or standard form, you have the ability to express the equation of that line in some form that relates to the Cartesian plane. Today, we're going to look at how we could express that same line using vectors. To do that, we're going to have to define or put some restrictions on these points. I'm going to refer to A as a fixed point, and I will refer to R as a general point. So here I'm going to draw in the position vector of A. That's the vector that goes from the origin to the point A. And I'm actually going to label it as vector A. I also have this vector, the position vector for my general point R. It's going, again, from the origin to the point R, and I'm going to call it vector R. The vector B indicates the direction of the line, and it can actually help us create a vector equation. Based on what we have here, it looks like what we could say to create a vector equation is that the vector R is equal to the resultant vector of A plus B. What this is actually saying is if I follow along from the vector A and then the vector B, it's going to get me to that general point here on my line. Consider if my point is actually at R2. And so let's say that the distance from A to R is the exact same distance as A to R2. So now my vector R going to my general point isn't going to be this vector, it's going to be this vector. And so now it's not A plus B that's going to get me to R. It's actually going to be A plus negative B. And so here, my vector equation for R, my point at this new location, is actually A minus B instead of A plus B. Let's consider now a completely different position for the point. I've labeled it as R3. R3 is halfway between A and R. So if I look at what sort of vector equation gets me from the origin to that point, I can still go along the vector A, but now it's not going to be a matter of adding B or subtracting B. I'm actually adding half of B to A to get my vector R. So the idea here is that no matter where you place your general point on the line, you can always find some sort of vector equation to get there. The vector equation that gets you to your point R is always just going to be R is equal to that position vector that gets you onto the line in the first place, so moves you from the origin so that you're actually on the line. And then you're going to add on that vector that's in the direction of the line multiplied with some sort of scalar multiple value. And that value can be anything. So this quantity t could be any real number. And by multiplying by any real number, it allows me to get to any of those infinitely many points along the line. So again, R is a position vector that's pointing you to any point on the line, a general point on the line. A is the position vector of a fixed point on the line. Again, that's the vector that gets you to the line in the first place. And the vector B is the direction vector for the line. So it tells you what direction you move when you're on the line to get to all the other points that are on the line. In general, in 2 dimensions, if we want to find the coordinates of a general point R, which has coordinates x and y, we would need a point on the line with coordinates a1 and a2, and a vector that indicates the direction of the line with components b1 and b2. If we have that information, then a more direct way of writing the vector equation of the line is the vector xy, that's the position vector for my general point, is equal to a1, a2 plus t times b1, b2. Now that's a vector equation of the line, but we can take that same information and represent it in a way known as a parametric equation. A parametric equation basically involves taking your x values, your y values, and expressing them as individual equations all on their own. So the x values are all independent of the y values. So I can actually read along the first row of this equation and establish that the x value for my point will be equal to a1 plus b1 times t. And similarly, the y value of my point will be equal to a2 plus b2 times t. So those are called parametric equations because t is the parameter that I use to actually solve for both of the variables. We can even use parametric equations to link back to our traditional Cartesian equations. All we have to do is isolate t in each of those parametric equations and set them equal to each other. So here I've isolated t in both equations and I'm setting them equal to each other, and now what I want to do is isolate y. So in this equation I've isolated y. It probably doesn't look in a form that you would think of as a Cartesian equation. But let me just simplify this a little bit further by multiplying that b2 into the brackets, and I end up with b2 over b1 x minus b2a1 over b1, and all of that is plus a2. And this is actually in the Cartesian form, although it might be a little bit difficult to tell. It's in the form y equals mx plus b, where this quantity here is m, or the slope. So by taking my direction vector and doing b2 over b1, I am getting the slope of that two-dimensional line, so that's very useful. And then this whole mess of parameters from the vectors is actually the y-intercept. The slope might be useful to find. The y-intercept, it's actually more trouble than it's worth at this point. So you probably wouldn't use that to find the y-intercept, but you would definitely use b2 over b1 to find the slope of that two-dimensional line. So if I wanted to find the equation of the line with a direction vector 3, 2 that passes through the point 5, negative 1, I now have a variety of different ways I could express this equation. I could write it as a vector equation. Xy is equal to 5, negative 1 plus t times 3, 2. I could express it as a parametric equation. X is equal to 5 plus 3t. Y is equal to negative 1 plus 2t. And I could express it as a Cartesian equation by isolating t, setting them equal, and then isolating my y value to end up with that y equals mx plus b form that we're very used to. These three forms of writing the equation of a line are all then clearly connected. Solving for a point on a line is actually fairly straightforward. You just plug in a value for the parameter, t or whatever scalar you happen to be using, and solve, and you'll get the coordinates of any point you want on the line. But verifying whether a point is on the line can be a little bit trickier. We're very used to plugging in an x value and making sure that the y value matches. But here, with that parameter at play, it's actually the parameter that we want to see that works. So if I want to check if negative 5, negative 10 is a point on that line we looked at previously, what I do is I plug in negative 5 and negative 10 for my x and y values on the left-hand side of my vector equation, or into my parametric equation would also work. In fact, we're kind of going to simplify it in that form in a second here. So if I look along the top row for all my x values, I know negative 5 is equal to 5 plus 3t. So if I solve for t in this instance, I get that t is equal to negative 10 over 3. If I look at my y values, I know negative 10 has to be equal to negative 1 plus 2t. And so as I isolate t here, I get that t is equal to negative 9 over 2. Now, while those values may be close to one another, they are not the same value. And because these t parameters are not equal for both the x and y value, I know that negative 5 and negative 10 is not on the line. The important thing to remember is that t parameter is the same t, whether you're talking about the x values or the y values, so it has to match up if a point is going to be on the line. As always, when we connect things to 3 dimensions, the rules for vectors stay pretty much the same. The vector equation of a line is still r is equal to a plus t times b, where t is some scalar multiple coming from the real numbers. Of course, now when I write my vector equation out in full, I have a z component to each of those vectors. And of course, then when I split them up into parametric equations, again, I'll have 3 of them now instead of 2. There are some distinctions that crop up in 3D. First of all, slope doesn't really have as much of a meaning once we're in 3 dimensions, so we're not really going to worry about how to express something like that. This is actually one of the key benefits of vector equations of a line, is that they continue to work in 3 dimensions, and higher dimensions for that matter, where other things from 2 dimensions would break down. We also don't take three-dimensional lines from their vector equation or parametric equation form and write them in a Cartesian form. It just doesn't happen for 3 dimensions, which is why I haven't written that here. Now, one final note about vector equations of lines, and it's something I glossed over at the start, but I'm going to clarify it now. Let's say I know I have a point that goes through negative 1, 3, and the point 3, 5, along the direction vector 2, 1. I've now given you 2 points that fall on the line. So as far as that starting point that you jump to, that sort of navigates you from the origin onto the line itself, you now have 2 different options that you could use. I could express a vector equation here as xy is equal to negative 1, 3 plus t times 2, 1. That's by using the first point to navigate me onto the line. But I could also make a vector equation using the other point to navigate me to the line. And that would also be a valid vector equation for the same line. Now you'll notice here I'm using different parameters for these equations. That's only because I've written out 2 equations of the same line using vectors. And I can't use the same parameter for both, because if I'm starting at the point negative 1, 3, obviously I'm moving different distances to get to each point, if that's my starting point, than if I was to start at 3, 5. Right? I might need to move 2 of the direction vector to get to a point if I start here, but I might only need to move 1 if I start at the point 3, 5. And so that's why those parameters are different. The interesting thing that comes to light here is I've written 2 distinct equations for the exact same line. That's something that we never actually had when we were dealing with 2-dimensional lines written in Cartesian form. Right? We would always write it as y equals mx plus b, and no matter how you actually got to that equation, it was always the same m and the same b if you were given the same information. What actually is really fascinating about vector equations of lines is, depending on the information that you're given, each person could come up with their own distinct equation for that line. There's infinitely many vector equations for a single line. It's just something that's really neat and really useful, because then you can express your equation in whatever way best suits what you're using it for. But it is also something that people might find just completely baffling why that level of complexity is necessary. And it's just sort of a natural progression of this system that we've built, and this way of analyzing things based on their distances relative to each other, that now, because we're not treating the line holistically in that slope-intercept form, we're actually saying you're starting here on the line and moving this way and moving that way. It actually does allow for that infinite range of equations, which is actually something, when you think about it, is very, very cool about vector equations of lines. So this topic for sure was a meaty one. There is a lot of depth to it. But the reason for that is because this vector equation of line idea is really the foundation for everything else we're doing with vectors. Coming up, we're going to be looking at more stuff in 3 dimensions, more applications where we model things with vector equations of lines, and all of those things will be built on this fundamental principle. It's really going to help us solve a lot of problems, but that's why this sort of takes so much time to digest, is because it's going to be pivotal down the road. We want to make sure we have a solid grasp of it before we get to those more challenging problems.